A very good morning to all the participants. I would like to welcome you all for this day 5 of this short-term training program on Industry 4.0. And today we have sessions with regard to 3D printing technologies. And the morning topic, we have Mr. Saksham Rastogi as a resource person from Altem Technologies. He'll be presenting uh, on exploring the possibilities of functional prototyping with FDM 3D printing. So I would like to give a brief introduction to Mr. Rastogi. Mr. Saksham Rastogi is basically serving as application engineer for the additive manufacturing at Altem Technologies. He is a 3D printing specialist and he has experience of both popular 3D technologies as well as mainstream 3D printing applications. He provides well-structured trainings and workshops for students and professionals on additive manufacturing. He has prior experience with association with IIT Roorkee. He was serving as technical officer at Rethink, the Tinkering Lab, and he was taking care of 3D printing lab along with CNC, VMC, Bio 3D printer, and industrial 3D scanners. So with that, I'd like to extend a warm welcome to you, sir. I think you can now take over the platform. You can present your screen and you can start the presentation.
Yeah. Thank you, sir. Thank you, Prashant, sir. Welcome to all the participants. And I would like to extend my thanks to the NMIT Institute and the whole team to provide us this platform to share the capabilities and possibilities with the FDM 3D printing solutions. So let's start our today's session. So just to give a small introduction about us, we Altem Technologies, we provide a complete 3D innovation platforms, and we are associated with many leading companies, industrial leading companies like Dassault Systems for CATIA solutions, for simulation solutions like Nestra and Adams for fluid dynamics or for manufacturing simulations. We provide solutions from MSC Software. Then for the plastic 3D printing, we are associated with Stratasys in India. And for reverse engineering and 3D scanning applications, we provide solutions from Artec 3D, which is a handheld 3D scanner. Then for the life science simulations like the discoveries, material developments or drug discovery developments, we provide solutions from Bivia Solutions from Dassault Systems. And for 3D bioprinting, we are associated with the Cell-Link Life Sciences. We are into the market since 2011, and since then we are able to bag various industrial awards like from MSME, Stratasys, Frost and Sullivan. So we look into our customers partial list. So this is our customers list where where we have provided the solutions to various industries like automotive OEMs, Ford, Ashok Leyland, Hyundai, automotive suppliers, and also to the educational and the research institute like NSIC, IIT, CTTC Bhubaneswar, VIT University, Jadavpur University, and many more. So let's start with the introduction of 3D printing. So what is 3D printing? 3D printing is a manufacturing process which enables us to make the product without any toolless technology. Here we synthesize our physical object by deposition or addition of material layer by layer. So what happens that from a CAD data, the CAD data, it divides into various number of layers depending upon the size of the object and also the layer thickness of the printing technology you're choosing. So after that, the slicing of the CAD file, the layers of the material, it deposits one by one, and the addition of the layers, it contributes to forming of a final object. But there is also one more term, which is additive manufacturing. So additive manufacturing is a complete process where 3D printing fits inside its solution. So in additive manufacturing process, we start from the design. That design we can optimize accordingly which technology we are choosing to manufacture it. And we also have software through which you can do the simulation and pre-processing of the object. You can look into the thermal stress and also the variations in the temperature of the whole object. Then after doing the simulation and the design optimizations, we 3D print the object. Then after 3D printing, we have to post processes. Post processing requires your finishing, cutting out the extra support materials, and give it a finishing which can be used for design validations or as an end use part. So 3D printing is basically a process which fits inside the additive manufacturing process. So you can look through the example in the photo that we can optimize our solid objects which we manufacture through our subtractive manufacturing processes or conventional manufacturing process. And through the additive manufacturing, we can reduce the material consumption, we can make the part lighter, and we can optimize the cost and the designs. So this technology gives a very much design freedom to the designers and the manufacturers, through which they can optimize and make it more ergonomic, the design, and also make the cost, they can reduce the cost of manufacturing. So if we look into our manufacturing challenges today, then the first challenge is to cost to build. So there are various in the manufacturing process. We have lots of tools and jigs and fixtures, and also the automation line components or end use part, end of arm tools for robotic automation. So for that, the tools or the fixtures, they require a lot of cost to build and time also. Then again on the heavy materials, so instead of using the steel, aluminum or solid block of metal materials, we can use the plastic materials now. So we have some super polymers where through which we can replace the metal end use parts or the metal tooling or fixtures onto the manufacturing floor. Then also the operator requirements like the lack of design knowledge, weight, size, shape, and production errors. So these kind of errors which can be happen with the operators on the manufacturing floor, these can be minimized. And also the productivity. So the tools which are heavy, which are made up of heavy metal materials, they are not ergonomic. They provide a very poor ergonomics on the manufacturing floor, and it can cause fatigue also to the users or the operator. And also the automation speed is limited by the weight of the tool. Okay, so if there is a heavy metal tool is using on the manufacturing floor, so it's lifting, it's whether you are lifting it through the machine or by hand manually, so it can reduce the ergonomics, it can provide very poor ergonomics and can slow you down on the manufacturing floor. Then the lead times. So the lead times for the manufacturing, for the automation tool lines like jigs and fixtures or for the quality inspection tools, it takes a lot of lead time to manufacture it and then use it. So the tools on the shop floor, it takes weeks to months also to produce it. But all these challenges can be taken care by the additive manufacturing, which has been considered a technology under Industry 4.0 around the world. So this technology can help to reduce the cost by 40 to 90% for your prototypes or for the tooling parts or for the end use parts. It can make you can replace the metal parts with the polymer parts, which can make the component 3 to 7 times lighter. So we have the engineering grade thermoplastics. We have 20 plus FDM materials available with Stratasys. And in these parts, we can modify the designs. We can modify the infill density of the material, which can help making the part lighter and make it more ergonomic on the manufacturing floor. Then, considering the of the operators on the manufacturing floor, we can reduce the safety issues. We can improve the ergonomics. We can customize the geometries, which provides much more efficient and much more ergonomic for the users. We can increase the productivity, so we can reduce the cycle times of the production. We can make the lighter end of arm tools for robotic automation. We can optimize the designs by considering the additive manufacturing design guidelines, and we can also make the accurate part, and also we can reduce the bill of material. So suppose if a part consists of 10 to 15 assembly components, okay, so with additive manufacturing we can reduce the number of assembly parts, and we can make one part, uh, we can make the one part integration. So like in the photo you can see this fixture tool is the symbol fixture tool, or you can say the logo fixture tool for the automotive industry. So this in this example you can see there are very less assembly components. So this whole white structure is 3D printed in one shot. So this kind of tools can be made with one shots, and we can reduce the lead time from weeks to days. So there are some examples where the customers are able to reduce the lead times about 70 to 90% on the manufacturing floor, and making their production of the tooling in a faster manner. So if we let's introduce about our Stratasys FDM technology. So FDM is fused deposition modeling, which was invented by Mr. S. Scott Crumb. He's a founder of Stratasys, and he founded this technology in 1988. So this was the second technology which was invented for additive manufacturing, and this technology was patented in 1989. From 1992, they're into the market selling their first 3D printer. And since then, they have developed a lot into the machine and into the materials that are available. So like to make the work process simpler, they have included the water soluble support materials, and also to maintain the temperature inside the machine, they have input oven type print chamber for printing of high temperature materials.
No audio, sir.
Sorry, so there is just a technical glitch. Just give me a minute here.
Okay, okay.
Yep. Yeah, sorry. So fused version modeling, this is a technology where you use the polymer in a the thermoplastic polymers in the filament form or in the wire form. So in this technology, the filament or the thermoplastic polymer, it converts into the semi-liquid state, and it extrudes through a nozzle with a computer control tool paths to build the parts layer by layer. So this entire process occurs inside a hidden oven type chamber. Okay, so this chamber is very much required to maintain the ambient temperature according to the which material you are using.
The part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer.
So as you can see, it uses dual nozzle system where one nozzle is for model material and others for the support material. So this support material is basically the dissolvable material. So it's just a small demonstration video about what is the technology FDM and what are the materials that we have and some of the parts.
Fused deposition modeling is a 3D printing method that makes durable objects out of the same plastics you see in everyday products. With FDM, the 3D printer takes a spool of plastic filament, melts it, and extrudes it onto a tray to build a part layer by layer from the bottom up. FDM materials are all industrial-grade thermoplastics. That's what makes the resulting parts so tough. And it's also why FDM is changing the way industries design and manufacture. With FDM, a designer can sketch an idea and test it the same day. Industries can cut lead times and costs. Products turn out better and get to market faster. FDM parts are helping to build the cars you drive. They're in the airplanes you fly in. They're in the medical devices that save lives. FDM is cutting waste in manufacturing. It's helping engineers power remote villages in Africa. It's helping farmers feed an ever-expanding population. And the ideas keep coming.
So in our Stratasys FDM technology, we have a variety of materials, starting from the standard materials, which are the ABS and the ASA materials. So ABS is a very standard general polymer material, which has been used in the automotive industry to make the rigid and the strong parts. The ASA material is developed by the Stratasys, which has a similar mechanical properties to ABS, but this is a UV resistant material. So UV resistance means you can test out the prototypes and even make the end use parts, which can be used in the outdoor conditions and can maintain the finishing and also the functionality of the component without any deformations or the warpages to the polymer. Then we have the engineering materials where we require more strength and more rigidity and various good mechanical properties. So we have the nylon 12 material, polycarbonate, and a composite polycarbonate ABS material. And we also have the biocompatible material, which can be used in the healthcare industry, which is a PC ISO material. For high performance materials, which can be used for high functional testings or to make the end use parts or for the tooling applications for automotive, aerospace industry, and for various manufacturing technologies. We have Ultem 9085, Ultem 1010, a PEC based material, which is Antero, a nylon type carbon fiber composite material, nylon 6, and also a special material for tooling application, which is called as sacrificial tooling. So we have a ST130 material also now with us. So what makes the Stratasys machine an industrial grade machine? Why the industries are adapting this technology is their key process control features and also their workflow, their easy workflow. So we have the motion control components which are thermally isolated from the build chamber, as this build chamber can go up to the temperature of 250 degrees Celsius to 300 degrees Celsius. And because of this high temperature, the motion control components or the electrical components can be damaged with this high temperature. So the Stratasys has patented this control feature, this technology, and they have isolated all the electrical components or the motion control components outside the build chamber, so that your machine can go for a longer life. It can run for 24/7 on the manufacturing floor. And also the basic, which are the very important features like the high temperature self-adhesive build tray, or the separate toggling and self-cleaning feature for the tips for model and support material, the multiple material channels with auto swapping technology, and also the automatic material feed, which can tell the user how much of the material is remaining, or you need to change some material before starting the print job. So the work process is very, very simple here. So once you have the CAD data with you, you can load up into the GraphCAD print software, which is a slicing software for the Stratasys machine. In this software, you have to give the orientation and some printing features, printing settings, and you can shoot for the print into the machine after that. The machine which will use the model material and the soluble support material for the overhangs or for the undercuts inside the geometry. And after the printing, you can we put the part into the agitation tank, which has a chemical solution of sodium hydroxide and sodium metasilicate, and this soluble support can be dissolved into the solution within a few minutes of time, and you will get a final part without any support marks or without any support structures inside the geometry. And this part you can use for your further validations for design, functionality, end of use parts, or directly as a tool on the manufacturing floor. So the applications that can be done using the FDM technology is first the prototyping, rapid prototyping. So for the design and the functional validations, we can use it onto our shop floor and R&D departments. For rapid tooling application, so we can bridge the gap between the complex tooling structures and the high lead time or the cost involved for developing of the tooling applications on the manufacturing floor. So we can make the customized tools, and also we can use it for the manufacturing process like the sand casting, or for the thermoforming application, for composite tooling applications directly. Then we can also do the rapid manufacturing. We can make the customized parts. So in some of the cases, the customer do not require to go for the mass production. So the condition or the application where you need to produce like 50 to 100 parts or 200 parts for the customized batch manufacturing, for some of the industries like the automotive, healthcare, aerospace industries. So we can use this technology. We can reduce the cost of tooling. We can reduce the cost of manufacturing. We can also reduce the lead time of manufacturing of the customized batch manufactured parts. So into the industrial applications, we can use it for the prototyping for large parts, like the front fender or the rear fenders of the 4-wheelers, 3-wheelers, or the 2-wheelers automotives, and for the functional prototypes for the engineering solutions for the design and production. We can use it for the jigs, fixtures, and the tools application, like we can create the patterns for sand casting. We can make the fixtures that can be used on the CNC machines. We can make the end of arm tools for the product line automation. We can make the composite tools, gauges. We can do the high and low temperature masking. We can make the protective parts with the composite nylon safe material or the elastomer materials. We can also use it for the production parts, like for the spare parts we can make, which can be used for the batch manufacturing. We can make the parts which require less than 1,000 volume in numbers, and also we can replace the metal parts with the high functional polymer materials like composites. So if we look onto the manufacturing floor, so generally we have some of the departments where we can utilize this machine, we can utilize this technology. So first of all, we can use it for on the assembly floor for the tooling application, where we can make the customized parts or the fixtures for the automation line, or for the end of arm tools for the robotic automation systems. We can use it for the R&D applications, for the product development, and also for the tooling development on the manufacturing floor. We can also use it for the quality control. We can make the customized holding devices or the measurement aids, and also the customized gauges also for the quality control inspection. And we can make the packaging devices. We can make the packaging trays for the particular spare parts or the components which require the very safe handling on the manufacturing floor. So we can make the customized packaging trays for the manufacturing floor. We can also use it for the safety engineering or for the health and safety departments, where you can use this technology to make the customized tools to provide the safety and the more ergonomic in the production environment. And also we can make the equipments for the robotic and also for the SPMs, special purpose machines, where we can make the components which are functional, which can be considered as an assembly, or where you provide a very heavy strength or need to replace the heavy metal parts instead of the super polymer parts. So the applications that can be done for the automotive and engineering applications into the industries, like for the styling applications. So the styling applications which requires the color combinations or the texture combinations for the exterior or the interior stylings of the automotive. So like the tail lights, fog lights, your control, your center consoles or dash panels, gear knobs, door handles, or the complete door or the seating engineering system also. So we can use this technology for the complete automotive developments. We can use it for the form and fit prototyping, for the functional or the performance parts, for the tooling solutions on the factory to make the jigs and fixtures, to replace the metal parts with the polymer parts, and also for the mold tooling applications. So like the sand casting, composite tooling, sacrificial tooling. So in these applications, we can use the FDM technology. So this is the first example where you can see a complete dash panel. So this kind of the complete dash panel where you need to make a large dash panels for the four-wheelers, and where you need to check all the component fitments which goes into the dash panel. So we can use this technology to make large prototypes, and also we can check the fitments of the smaller components which goes into the dash panel. So this panel, this center dash panel has been 3D printed with the UV resistant ASA material, which provides a very nice matte surface finish, which are the basic needs for the designers into the interior applications. So apart from the interior parts development, we can also use it for the exterior styling developments. So like the dash panel, center consoles, AC vents, or the front vendors, rear vendors, fog lights. So we can use this technology. We have the lumps which can print 1.4 meter of total length with our Stratasys F900 printing solutions. So this is a front grille which is printed in F900 in less than 24 hours, which conventionally can take more than a week or 2 weeks and even a month also to make the customized or the prototypes for these kind of large prototypes or large components. So we can reduce the turnaround time by 50% compared to the traditional methods. And also we can accelerate our time to market to launch the products which can make an impact onto the business by launching your products earlier into the market. We can also make the texture parts with this FDM technology. The photo that by using the which provides a very good surface. There are companies who are making the customized solutions, customized front grills or the interior parts for the customers who provide the customized solutions. So we have the ASA material which comes in the 8 colors, and we can print any kind of the textures over it. And this part can be fit directly onto the four-wheelers or the two-wheelers or any of the automotive vehicles, and it can be directly used and customized accordingly as per the users. So apart from the passenger vehicles, what we can do, what sort of developments we can do in industry in the perspective of the engineering and the automotive part developments. This technology can also be used for the mobility transportations. So like the commercial vehicles example is first is Ashok Leyland. So Ashok Leyland has adapted this technology, and since for last 4 years, they are using this technology for the complete product development, whether it's under the hood engineering parts like the gearbox casing to check its fully functional mechanism. So this is the data given by them, which I mean, for the gearbox, conventionally it used to take 45 days for them to develop it. And with the 3D printing, they reduced the turnaround time about in 40 hours. So there is a 90 to 95% of reduction of lead time into the product development. They are also making the clutch housing development for gearboxes and the blower covers for the cabin interior parts. So this technology Ashok Leyland is using since last 4 or 5 years, and they are able to save a lot of cost and a lot of lead time, and they are also using now for the development of the electrical vehicles or the e-mobility solutions now to fasten up their product development and to launch the part into the market, to launch their product into the market as compared to their rival companies first into the market. So this is another example from premium transmission, which makes the complete gearbox, or you can say the complete mechanism of the gear generations or the gear components. So with the traditional method, they used to make the scaled down components in 42 days, but with the FDM technology, they are able to make within 4 to 5 days. So you can see that the complete mechanism, the complete assembly can be created, and you can fit the bearings, or you can also use the fasteners to join the components together, and you can check its functionality, its design, the tolerances between the components and its functionality and movement before you finalize the design and before you go into the final production. This is another example for the end use part application. So there is a company, Angel Trains, which is from the England. They make the passenger train, and they also make the components for the interior and exterior for the passenger trains. So you can see they printed the armrest, grab handles, and the table trays, and these 3D printed parts are directly fitted and used into the transportation systems for the passenger trains, like the 3D printed grab handles also. So these polymers, these thermoplastic polymers are providing a very good strength and capability to reduce the metal parts, and also enabling the user or enabling the organization to go for the batch manufacturing by reducing their lead times and also the manufacturing cost. So these are some of the examples which can be manufactured or which are being manufactured, and they are being used into the transportation systems. So like the cable clips, connectors, or the brackets can be manufactured by using the Ultem 9085. The HVAC air duct systems can also be manufactured. Handle safety systems, uh, where you can make the part with the Ultem 9085 material, and you can wrap around the glass fiber or the carbon fiber sheets around it and make it more strong for the final end use parts. So like TV screen housings or the electric cable holders, individual table, seat armrest. So these are some of the examples for the interior. And if we look onto the exterior side, the lighting or the sensor housing, large covers, which are more than 1.2 meter to 1.5 meter, we can use the composite material like nylon CF, and we can wrap the glass fiber sheet around it to make the part more uh, to give the part more strength for the final end use part. Front bumpers with the Ultem 905 material, air vent systems, and also the hand lamps housing. So these are some of the components which are being made and used as an end use part in the transportation systems. This is one more example from the GVL Poly, who makes the agriculture equipments. This is a US based company, and they are using the Stratasys FDM 3D printing. And this is a one shot video. So I'll just play this.
Poly is a custom rotational molding manufacturer. With our 3D printer from Advanced Tech, we've really changed the concept of what GVL Poly is and what we can be. In working with Advanced Tech, our processes and our concepts, our parts that we've produced here at GVL Poly are far more complex than they were before we had 3D printing. Printing's enabled us to really think outside of the box. And at this point, there'd be really no way for us to go back and look at manufacturing at GVL Poly without our 3D printer. Our most recent advancement for corn harvest has been improving the wear tip. It has to be able to keep all of the corn feeding into the corn header. It has to be able to collect the crop without folding underneath and damaging the crop or the corn header. So we're taking a product from a 3D printer, we're bolting it on to a piece of harvesting at constant contact with the ground. It gives us all of the testing that we need to do to test fit, form, and function. Without the 3D printer, without being able to do those revisions in very short order, and have a product from the printer that we can field test, it would have drawn a project like this out 3 to 5 years. We were able to do it in one harvest season and test dozens of variations of this wear point. One of the other innovations that we've been working and doing with our 3D printer was on the end of the corn header, we're able to produce an auger to help pull in the down crop. Print several models, get them out in the field and test them. Help the farmer pull the crop in during that harvest season, make modifications on the fly. As a former banker and now CEO of GVL Poly, we really looked at the return on investment of 3D printing in a much larger picture than just the standard production equipment. When we brought in our 3D printer and showed them that we, as a small company, could invest in cutting edge technology and give us a very expansive product offering capability, it helped us get the employees to believe in where we were going. In the last 2 years since investing in our 3D printer, we've added 7 new positions based on the new demand that we have in that area. We also have added additional manufacturing jobs related to new product coming out on the floor much faster than we would have in a normal prototyping or R&D setting. All of the support we receive from Advanced Tech, whether it's design or looking at the 3D printing technology, is really something that we just can't live without at this point. Having our printer in-house and having that available at any time 24/7 to our designers and engineers has really been a game changer for our team. Not having to wait for some other service provider to have time available or to figure out how the design will print. All of the software, all the engineers and designers of the 3D printer are in one location so we can utilize it to its fullest potential. Crop farmers plant in the spring and they harvest in the fall. Their entire living is based on a risky proposition. They have to have the right tools. The demands are getting more and more on the farmer. Our reaction time, our time to market has to be shorter and shorter. So we're able to do that with 3D printing to make sure that we're giving the farmer the best they can have to make food and crop. GVL.
So you have seen that not just for the passenger vehicles or for the commercial vehicles, but also for the agriculture industry also, we can use the Stratasys FDM technology in a much more efficient manner, and the in-house capability provides the users or the organization to make and to launch their products in a faster manner. So there is a faster time to market funda in the organizations. So by using the 3D printing technology, the FDM technology, we can do the design and the functional validations in the real-time conditions, and we can make the product development in a very much faster manner comparing to our conventional processes, which can takes a weeks or months of lead times to develop the product, and it slows down the launch of the product into the market. So this one more example is from the Minimizer trucks. So this is a company who uses a Stratus FDM solution and provides a better truck solutions with a minimal cost. So this is a short video of how they are using the Stratasys FDM technology and how they are doing the functional testing in the real-time conditions.
My name is Craig Kirkwood, CEO of Minimizer. We are a manufacturer of plastic truck parts in the heavy truck industry. We've been in business since 1984.
Here at Minimizer, some of the projects that we work on are injection molded components. And primarily right now, we're looking at several mounting brackets. A lot of these parts are made from glass fiber and rough, rugged plastic materials. And so it's a challenge to prototype those products. With the Black Ultra material, it's very high tensile strength and rigid. We found that Black Ultima is a good alternative for us to prototype these mounting brackets and even take them out into the field on a truck and test them out. When we make an FDM part, we mount it on a truck, so a lot of times there'll be a lot of drilling using fasteners, even mating parts together. The Black Ultra material is valuable because if there needs to be any sanding or cutting of the part, it allows us flexibility to do that, but still have an aesthetically pleasing part to put on the vehicle.
The reason for the Black Ultra, and we're excited to see that, is that's 90% of the color of my product in our industry. We caught one of our OEs actually using the product in boat trials with the Ultra, and they decided that in this application, we don't need that many to tool up for it. So if you could just print us out 15 of these for a military contract, and they just need 15 units right now. So they said, okay, give us that part back. We'll give you the Ultima in black. And so that's when we found out that this came out. We were going to paint it, but now that it's coming out black, we're going to paint it.
Having the black material is a big bonus for us. We don't have to spend the time to finish the part. And at the same time, we get the same material properties that we look for in the Ultima material.
Okay, so you have seen some examples from the automotive industry that how the commercial vehicles or the passenger vehicles and also for the agriculture equipment product developments, we can use the FDM 3D printing solutions with engineering plastics to the high performance materials, and how we can use it just not for the prototyping purpose, but also as an end use parts into the interiors or for the exteriors components for the mobility transportation systems. So now if we look into the aerospace applications, so there is an e-mobility electric aircraft company, Aviation, who uses the 3D printing technology. They have developed of the parts. So this one from the inventory that they have made up a composite layout tool using the Ultem 1010 resin material for the production of the carbon fiber parts. And in this 2 years of operations, they were able to save $100,000 and also the 6 months of the workforce hours. And also for the e-mobility, we can use it for the battery housing developments. So nowadays the e-vehicles or the e-mobility solutions are very popular into the market. There are various organizations are coming into the market, and they require, and some of the organizations have adapted already from e-vehicle systems this technology, and they are able to minimize their lead times for product development and also to save the cost by using the various high performance materials like nylon 6 material, which is a very good and a functional material for the battery house developments, because battery housing requires much a lot of weight to contain it, and nylon 6 material, it is capable to withstand that weight and provide the good strength, and also enabling the designers to make different kinds of the designs which are ergonomic and which can reduce the manufacturing cost. Then there is an organization called Boom Supersonic. The Boom Supersonic, they make the aircrafts, and it's a US based company. So they are using this technology. On the screen, you can see that this is their facility setup. So they have a big F900 machine, which is a production level machine, and one Fortus 450, again a production level machine, and also a office friendly machine F370. And they are using these three machines, and they are making the functional prototypes, and you can see in the photos that they have made hundreds of jigs and fixtures and tools, and also the flying parts for their aircraft developments. So this example is from the United Launch Alliance, which makes the coolant supply tubes for the space applications or for the aircraft applications. So in this application, you can see in the photo on the right side that there's a metal coolant supply tube which fits on the base of the rocket launch vehicle, on the outer periphery of the rocket launch vehicle. The conditions are there of the high temperatures and the high vibrations. So they have used the Ultim 1010 Aerospace approved material, which enable them to reduce the weight, to reduce the number of assembly, and also the reduction on the assembly cost. So they were able to reduce the number of assemblies from 140 to just 16 parts by using the FDM technology, and also the cost of manufacturing reduced to 57%. So not just for the high engineering applications or for the automotive applications, but you can also use it for the developments of the UAVs or for the drone systems, or the complete chassis or the body of the drones and UAVs. So this one company, Aurora Flight Sciences, they make the commercial UAVs, or for the commercially, and also for the defense organizations. They develop the customized UAVs and the drones. So they are using this technology, and they are also able to cut down the assemblies. So instead of and this complete UAV has been consist of 34 components, out of which with 3 liters of the fuel. So the benefits that they've got is that they are able to cut down the build time by 50%, and also eliminating the tooling which help to reduce the lead times for their production. So there are various examples for the 3D printed drones. So many of the organizations and the research institutes, they are making either the 3D printed drones or the components, customized components, or the mountings which can be fit onto the drones and can be used for the various applications. So like for the surveillance systems, and also for the agriculture system. So for the agriculture industry, now drones are being used in a very efficient manner. On agriculture, on the fields, we can use the drones in various applications, and we can use this technology to make the customized components or the end use parts to be fitted on the on the drone systems, and we can utilize the drones in a much more efficient manner now. So apart from the end use parts or the rapid prototyping solutions, you can use the FDM solutions for the automotive assemblies or for the tooling applications. So this one example of the tooling applications for the screen wiper assembly, which is around a 1 meter in length, and it has been made in nylon 12 CF to provide a good stiffness and more strength into the part. There's a brake pedal assembly tool which weighs around just 230 grams, and there is a leaf spring assembly tool, again manufactured in nylon CF composite, which is 3 times lighter than the metal tool. For the automotive dry lines, for the greasing jigs, for the end of arm tools, it can also be used. So the Ultem 9085 material is a chemical resistant material, so you can use in the application where you require the greasing process or the greasing functionality. It can reduce the 70% in the lead time of the manufacturing, and also it enables to make the complex assembly tools which can be manufactured with a fraction of the time comparing to the conventional manufacturing process. For the end of arm tools, for the automation systems like the clamping tools or the mounting tools or the holding tools, we can use the Ultem 9085 to provide more strength, good thermal resistance, and also good chemical resistance, higher stiffness, and we can replace the metal clamps by using these polymer parts. So for the tooling applications, John Deere globally and in India also, they are using on the for the factory floor tooling solutions. They are making more ergonomic and lightweight tooling solutions by replacing the conventional aluminum or the steel fixtures or the jigs, and they are able to reduce the weight of the tools, large tools, and also its cost of manufacturing by a very long margins. So apart from the rapid prototyping and for the tooling applications, and also as the end use parts, there are some of the tooling areas where you can use this technology on the manufacturing floor. So first of all is the jigs and fixtures. So we have seen many of the examples for the jigs and fixtures. So the basic challenge that comes with the fixtures is of the large components of the large fixtures, okay, which are more than like 2 meters or 3 meters, and this is one of the examples of them, which this is a steel fixtures which weighs around 80 kg, and the fabrication is used here, the CNC machining and the welding, which can take like 2-3 weeks or more than that in the manufacturing process. And this kind of conventional processes, it provides a very poor ergonomics on the shop floor. So 3D printing fits into this solution because we are able to do the optimization for the shape, for the design, so that we can reduce the material consumption, we can make the part lighter, we can also optimize the infill of the material into the design, and we can optimize the material, like we can use the Ultem nylon CF material for the lighter weight parts, which can provide a good strength to weight ratio in against of the metal fixtures, heavy metal fixtures. So the benefits that you get are the low cost, on-demand solution, ergonomically friendly, easily iterated, consolidated assemblies, and we can reduce the lead time by 2 days or 3 days instead of the number of weeks or months. We can reduce the weight and we can make it more ergonomic. So this is one example for the tooling solution, this one company, Solexis. They have replaced the metal fixture which weighs around 68 kgs to 12 kg of the final fixture tool using the FDM solution. They're able to reduce their lead time from 16 to 20 weeks to 3 to 5 weeks. And they're also able to achieve their ROI within 12 months. This example again is from the BMW for the jigs and fixtures. So this is a logo fixture. And the challenge was the traditional fixture was very heavy, which was made into the aluminum material, which weighed around 16 kgs. And with additive manufacturing, they able to reduce the weight by 1.4 kgs. So it's a lot of reduction when it comes to the weight or to the production time. And also it provides a good ergonomics and less fatigue to the operational users. So these are some of the examples where you can make the customized tools and fixtures and the end of the arm tools for the robotic applications or for the assembly systems or for the manufacturing systems. And also for the quality control, so like the CMM inspection fixtures, customized gauges, and the packaging trays, and also the elastomer materials where you require the soft and the flexible assembly tools like to place the badge on the motorcycle tanks without damaging the painted surface of the engine tanks. So it can also be used for the sheet metal forming. So the fabrication that takes conventionally is through the CNC machining and the pressing. Used for the tooling is metal, and the lead time takes to about 2 to 3 days, and also it also involves a very high cost in the traditional process. But with the FDM 3D printing solution, you can make the 3D printed tools for the sheet metal forming. You can use the engineering and the high performance material. You can use it for the tonnage rating of 2 to 3 tons per inch, and we can produce a low volume of the production like 500 to 1000 pieces with a single tool here. So the application where you don't require a mass production, or you want to test out the tool before making into the final production, you can use this technology for the material like steel, stainless steel, and the aluminum. So you have seen that this is a 3D printed tool fitted on the press machine, and you can see all the components or all the systems like the ejection systems or the controlling systems are all fitted on the press machine, and it is capable to do the sheet metal forming manufacturing for like steel, stainless steel, and aluminum to about 2 to 3 mm of the sheet thickness. So this is one case study from the steel wheel manufacturing. So they are the manufacturers through this for the sheet metal forming. So the benefits that they have got is the customizable tooling application, and also the in-house capability for the 3D printing and for the low volume production. So for where the condition arrives of low volume production, we can use this technology to make a cheaper tool with a very good strength, and where we can make the parts from 500 to 1000 pieces of the pieces for the solution. And we can use it for the thermoforming tooling application also. So in thermoforming, we use a plastic sheet and we place it on the tool, and by the application of the heat and the pressure, the sheet takes the shape of the tool. So in thermoforming, the traditional process is through the fabrication of CNC and the manual processes. The materials which are typically used into the market are wood, plaster, epoxy resin, aluminum, or foam. And the process for their production or for the assembly time, it takes from days to week. So these kind of challenges can be replaced or can be catered through the 3D printing application. And this thermoforming applications can be used into various industries, like for the packaging, for the cosmetic cases, food containers, for the medical industry, computer electronics industry, machinery, and plumbing. So this is one short video by showing how you can make a 3D printed tool for the thermoforming, and how it can be used for the thermoforming application. So the 3D printed tool is placed inside the machine, and this is a plastic sheet placed over it. So now this plastic sheet will go under the thermal condition. It will get softened up to a temperature. So with the apply of some pressure here, this sheet takes up the form of the tool here. So you can see that even the plastic made tool can be utilized to make the tooling for the thermoforming application. So there are some industries globally and also in India who are using this technology for the thermoforming application. So you can see that the finishing or the end product through the thermoforming tooling. So this is one company called Kins Plastic who makes the thermoform trays. So the challenge was what they're facing were the conventional method was very costly, and also it used to take around 6 to 12 weeks of the tooling development because of the more complexity and the availability of the CNC or the conventional manufacturing machines. So this part consolidation, what the benefits that they have got is the weight reduction, first of all, by replacing the heavy metal tooling and to improve the efficiency, and also with the sparse fill capability, they were able to they don't need to include any vacuum channels which were required and which were very difficult for the conventional manufacturing solution for the complex tools. So they were able to reduce the tooling cost and the lead time by 50 to 75%. We can use the FDM printing technology for the sand casting solution also. So in sand casting, we make the patterns and we pack the sanding material, the sand material around the pattern, and we make the cavity. And this cavity we pour the molten metal material to get the final metal object. So the solution which can be done through FDM is we can print the low number of volume like 5,000 plus casting parts. We can make the prototypes and the pilot runs from low to moderate solution. It can withstand the compaction pressure of around 3000 psi, and it can be used for the moderate to high complexity designs or the pattern solution. The material which can be used to make the patterns are the ABS material with the compaction pressure of around 3000 psi, polycarbonate material for the pressure up to 6000 psi, and ultim material which is the strongest material and which can withstand the pressure of around 10,000 psi for sand casting solution. So this one example from the Melron Corporation for the manufacturing of the door and windows hardware. So you can see in the photos that this 3D printed pattern in the white color, and the next photo is the cavity mold for the sand casting, and the third photo is the manufactured parts with the sand casting solution. So the benefits that they have, the challenges, first the challenge was the additional cost, which was around $5,000 or more than that, and it took around 3 to 4 weeks for the mold iterations, and also to make the runner and gate system, which needs to cut out separately for the sanding for the sand casting solution, and then add the match plate. But the benefits with the 3D printing that they have got is they can combine the cope and drag patterns in a single piece. So instead of doing separate cope and drag patterns, they are able to do it in a single piece solution. The material can withstand the abrasion pressure and also which is required for the packing the sand. and also the iterations are very easy. So to make the patterns against the conventional manufacturing process, the additive manufacturing process can provide a very faster iterations into the designs, and it can help to reduce the cost and the lead time for the pattern manufacturing.
Here at Melron. Melron is located here in Schofield, Wisconsin, which is the central part of the state. It's kind of the hub for window fenestrations, window making, commercial, residential, wooden, and aluminum. We had a customer approach us. They were in the final design stages of their window, and they were looking for a piece of hardware of ours to put onto the window. So what we did is sit down with them, look at their drawings, look at their crucial dimensions. Then we made a 3D model of the actual part and printed it off on the prototype machine and sent that to the customer for approval. They got back to us right away. Said, yep, absolutely, that's great, ready to go. Problem is, we have a very tight deadline. So can we speed up to get CAS products to us? This is our pattern shop. Once the rapid prototype is approved by the customer, what we'll do is a mini insert on a pattern. So we're not doing the full production tooling. We will actually throw it, in this instance, the left and right handle on a mini pattern and mount that into a match plate, which we will then cast to get actual cast samples of the part to then send to the customer for approval. Once we get approval from the customer, we have a blank aluminum billet that we machine the inserts out on our CNC or bridge boards for mounting of the FDM insert. Once these are printed off, mount them in, then we then start our post sanding and any other processes we need to be able to make the actual part. The challenges with the traditional method were that you had longer lead times and you were pretty much set on what you had with your batch plate because it's being machined out of aluminum. Where with the plastic, you're set, but at a very low cost, we can print something off, change our parting lines, change we're putting gating in very effective. With that particular project for the FDM, we saved about $3,000 per pattern, as well as about 2 to 3 weeks actually of lead time on the actual production tooling. We then want to come back to us again because it was a very easy process to work with. By using the FDM machine and material, it really revolutionized how our business is, being able to adapt quickly and provide a cost-effective part that is instrumental in us going forward.
So you can see in the video that the Melron Corporation, like companies like this, they're using the Stratasys FDM solution to make the sand casting patterns. So the materials like ABS, polycarbonated Ultem 9085, which are capable to withstand about 3,000 to 10,000 of PSI pressure, which is required to pack the sand around your casting patterns. So this technology can be used for the composite tooling solutions also. So for the composite tooling solutions, the challenges that they face in traditional process are first is the hollow composite parts trap tooling. So for the hollow composite parts, which can trap the tool inside it and makes it difficult to take out the hollow composite parts. The puzzle pieces course for the complex internal geometries, split molds, and also the post-curing bonding of the parts together. So the solutions that the Stratasys FDM has come out is the ST130 material, which is a specialized material for the sacrificial tooling for the production of the complex composite parts, which can dissolve in a basic solution of less than 7 pH value. So this material can provide the benefits to make the FDM course. So you can see in the photo that the left side is the tool produced with the 3D printing technology, and the right side is the composite fiber part produced by using the hollow composite composite part, which is produced by using the ST130 material. So we can reduce the lead times, cost, reduce the labor work where we can also reduce the tooling, and we don't require for the post-curing bonding solution. We can improve the quality by making a single piece composite parts, and also we can lower the risk for and provide the easy modifications. So for this solution, it best fits into the layer process, which could enclose the tool and completely and produce a single part. For the small quantity and the high value of number of parts, functional prototypes, and for the custom production parts, and where it is required the complex or hollow undercut parts. So these are the few examples that are being made by using the ST130 material. So we can wrap around the sheet of this tool, and this material can be dissolved in a basic solution. So you can see this is a work process here. So with the CAD data, you can make the tool, you can produce the tool with ST130 material, make it some finishing, wrap the sheet around it, and you can cure this sheet. You can cure this tool material into the oven by up to a temperature and pressure. And this ST130 material is a dissolvable material under a basic solution, and you get a final hollow complex composite parts.
Hello everyone, I'm Tim Schnipp. I'm the Composite Tooling Director at Stratasys. We're here at Sanpete, Long Beach 2016. We're launching our new composite tooling design guide, as well as our new sacrificial tooling solution. And here we have a few of those tools on display that we've developed for Dassault Falcon Jet. This is a high temperature layup mold, as well as another one over here, and then the associated low temperature machining fixture. So we've been working with this customer to really transform how they design their tools and make them suitable to the additive manufacturing or fused deposition modeling process. These are really great examples of the kind of the economic power of the solution too. With this particular customer, with the Falcon Jet, their existing tools cost about $50,000, $60,000 and take 10 to 14 weeks to acquire. We were able to print this tool in less than 2 days for a cost of about $3,500. So as you can see, a pretty disruptive solution there. Works really great particularly for lower volume tooling, but we're looking at it for production tooling as well with them. Really testing it out to prove its full capabilities. And then if we walk over here, I can show you a couple more examples. Here's our new sacrificial tooling solution. This is called ST130, as well as the comprehensive design guide that you see here that goes along with that. And this is an aero duct that we worked with Swift Engineering on in multiple stages. Here it is right off the printer. Here it is sealed and ready for layup. This is where the part is laid up on top of that mandrel or that mold. As you can see, there's some resin flashing here that once you wash away and show your final part here, that all goes away. This particular part went from concept design to tool in hand in less than a week, and the tool was laid up in 1 day and washed away in 8 hours. So really great time efficiency for this solution as well.
If you weren't using 3D printing, how would you have done that?
So you would use a traditional washout material such as like an eutectic salt or a low temperature plaster material, or you'd have to go to a combination of a hard tooling where you lay up in halves, the part in sections, and bond that together, which takes additional tooling, additional process time. In this case, you really go from CAD model to tool.
So you have seen that with the composite tooling solutions, there are many of the examples we have. So like the aerospace industries, where they are dependent on most on the composite tooling solutions. So like the Aurora Flight Sciences, Boeing, Airbus, Dassault Falcons, Champion Motorsports. So these are some of the examples where they are using the Stratasys FDM materials and solutions to make the composing tooling and the sacrificial tooling solutions, and they are minimizing and disrupting the manufacturing technology by using this the benefits of the additive manufacturing. So apart from the automotive engineering and the heavy engineering industries, it can also be used in the healthcare sections to make the anatomical parts, medical devices, for the anatomy testing, prototyping, or for the design and engineering applications for the medical devices, and also to make the patient specific tooling solutions like the fibula guides, implant molds, or the surgical guides. So there are two type of categories in medical devices. So like the general purpose medical devices like the ECG machines or X-ray machines, CT machines. So we can use this technology to make the product development uh, of these kinds of medical devices, to make the implants, to make the anatomical models, to check the fitments of the screws or the implants, to make the prototypes of the medical surgical equipments, and also to make the patient specific medical devices like the fibula guides or the surgical guides, which can be designed and fabricated as per the specific patient anatomy. And these are the biocompatible materials, so these can be fitted inside the human body or animal body, and can be used as the surgical guides. So these are some examples like for the orthopedic surgeries, we can 3D print the patient specific anatomies of the bone structures, which can be used for the condition in the bone cancer surgeries or arthritis, realignment of the deformed limbs, and also for the reconstruction of the fractured bones. So Medtronics is a company which is a world-leading surgical equipment manufacturer company. So they use this technology in a very efficient manner. Medtronics in US and India, they use the strategy solutions for the product development and for the prototyping solutions with the biocompatible materials like the PCISO, which is a USP Class 6 certified, which makes them enabled to test out their prototypes on the anatomies before going into the production application. And also they are using for the tooling applications also in the healthcare industry. In IIT Bombay, there is a lab, Batic Lab, which is funded by the Department of Biotechnology. Their basic agenda to develop the high quality, low cost medical devices, which is suitable for the local population. So there are Batic labs all around the India, all around the states and the cities, into various research organizations. And most of the Batic care labs, they're using the Stratasys machines because of the materials that are available, and also the strength and certifications of its biocompatibility. So the ABS M30I and the PCISO are very good, and the certified materials for the patient contact applications. So you can see in the photos that how they are developing their developing stages of their particular products. We can use it for the companies like the Oxygen Medical, who makes the customized implants, titanium implants for the patient specific anatomies. So they are using this technology to make the patient specific anatomies and to check the fitment of the implants before they produce it in the hard biocompatible metals such as the stainless steel, titanium, or the cobalt chrome, because these metals are very costly and their manufacturing process also very complex because of the patient specific anatomies. So first they make the anatomy of patient, and then they check the fitment of the implant which they have designed. So after the good fitment check, they produce the final implants into the biocompatible metals like titanium or stainless steel. So just to cover up or to conclude about this session, the benefits that we get from the additive manufacturing is, first is the flexible manufacturing. So we can produce any kind of the complex structure with this technology. The standardization of the manufacturing floor, no tooling cost, the cost effective solutions for the low volume productions, mass customizations, rapid turnaround time, efficient use of the high value materials, reducing the design limitations, complexity for the designs, give the complex design So I would like to thank all of you for being a very patient listener, and we can take up the questions now.
Request the participants to kindly post your queries. If you have any questions, kindly feel free to interact with the resource person.
Hello, good morning.
Good
Hello.
morning. Yeah.
Is there any similarity between this your 3D printer? 3D printer is generally used for prototyping. Is any similarity between your CNC machine and the 3D printers? Any similarities?
Sorry, can you repeat the question?
This your photo 3D printer is generally used for prototyping or any design, no? Before manufacturing bulk quantity. Is there any similarity between this CNC machine and your 3D printers?
No, there is no similarity. The difference is first with the CNC machining, you do the subtraction of the material. So you take a block of the material and you subtract the material to achieve the final geometry. But in the condition of additive manufacturing, it's addition of the materials layer by layer. So there is no wastage of the material or you don't require any cutting tool or the tooling fixtures to make for the 3D printing solutions. So yes, I mean CNC machining considered as a conventional or the subtractive manufacturing, and 3D printing is a additive manufacturing process. So there is no similarity between both of them. But yes, we can. There are examples that I have shown you where the organizations or the manufacturers, they are capable to replace the metal parts which were produced with a CNC machining by 3D printed thermoplastic polymers.
Yes. That's why I'm asking this question actually.
Yes.
Okay, thank you.
Thank you.
Sir, I have a question.
Yes.
Sir, in Ashok Leyland, does the
Yeah.
3D printing is used to design the engine parts of the vehicle?
Yes, so Ashok Leyland, they have adapted the Stratasys machine in-house since 2015 or 16, and since then they are developing the exteriors and the interior parts, whether it's the under the hood components like the gearbox mechanism or the engine mechanism or the engine designs, and they are reducing the lead time in the product development so that they can launch their product into a faster manner into the market. So yes, they are doing the complete R&D by using this technology in-house only.
Thank you, sir. Thank you very much.
Mr. Saksham, I have a question. This is Prashant from NMIT.
Yes.
So when we talk about FDM 3D printers, basically it is 3D printing the material in terms of layers, right? So
Yes, sir.
when it comes to material strength, let us take a tensile strength or a compression strength. So now what is the, even if we print a material at 100% infill density, does the 3D printed material, in what way it is comparable to the strength as against material which is, let us say, injection molded? So what would be the difference of strength, material strength?
Yeah. Thank you, sir. That's a very good question. So when we compare the 3D printed thermoplastic parts in comparison to the injection molded parts, so we have studied and we have also get the feedbacks from the customer that it matches 95 to 100% of material properties, which are basically which are available into the market. So like if I take the example of ABS, polycarbonate or the nylon material. So from basic to the functional polymers which are available into the market in the pellet form and which are being used through the injection molding process. So the strength is equal. So the 3D printed parts provides an equal strength to the injection molded parts now. So the strategist has developed their materials in a very much efficient manner so that they can cater the industrial problems, their challenges, while comparing to the injection molding process. So now the materials has been developed in in such a manner that you get the equal strength or sometimes more than the strength which are available into the market for the injection molding process. So that's why the companies are producing the batch manufacturing parts as an end use parts because they are getting the equal strength or they are getting the equal strength to the thermoplastic polymers or and also in some cases to the metal materials also so that they can replace the heavy metal components with the lighter weight thermoplastic solutions.
Okay, thank you. So, just to extend this question, so if I'm designing a 3D printing, a part for the 3D printing application, so naturally, I may not be using 100% infill density. So during material strength analysis, let us say if I'm performing FEA analysis or something like that, uh, when it is model is when the part is CAD modeled in the software, and then it is taken for the analysis purpose. In that phase, the 3D printing part will not be taken into account because finally when I 3D print it is a layered manufactured component, but during the analysis it is still a solid part. So if I have to analyze a component which has to be 3D printed, is there any specific software where I can factor in the layered manufacturing and then perform the material strength analysis?
Yes, sir. So we have the solution from the MSC software where you can use it's a Digimet solution, MSC Digimet software, where you can do the structural simulations and also the thermal simulations for the polymers for the 3D printing solution. So for the FDM technology, Digimet is one of the solution we recommend where you require to simulate the structural integration or the strength inside the part, and you can vary the infill density of the material inside the component into that simulation software. So yes, I mean for the simulation or for the pre-processing solutions, we have the software which enables the users to test out the components or to test out the infill density before actually producing the part.
Okay, thank you. So I'll take a couple of questions which has been posted by the participants in the chat box. So a participant would like to know what are the disadvantages of.
The first, and it's a very common disadvantage, is that 3D printing is still not developed for the high volume productions. Okay, so this is a question that we have been asked many times by the industrial users or by the manufacturers. We cannot produce high volume of productions like 10,000 or lakhs of pieces with a single 3D printed tool. But yes, where there is a requirement of the customized manufacturing of the parts, or say a batch manufacturing or low volume manufacturing of the parts, then 3D printed tool is a better solution and better and the cheaper solution when comparative to the your conventional tooling process. So this is one of the disadvantages that we talk about and which the OEMs, 3D printing manufacturers or the 3D printing solution makers, they are focusing on. But yes, it's a very long shot and it will take a long of time. But this is a very common disadvantage where we can say that it's not for the high volume production.
Okay, thank you. So there is one more question for the increasing the material strength in 3D printed material, what should be more important, the infill density or the shell thickness?
Okay. So it depends on few factors. So first is the what are the actions acting on that component. If there are some actions acting on some particular areas, then you need to increase the shell thickness to provide the outer structural integrity for the component and to disperse the stress inside the part. Okay, you need to make the infill not 100%, but yes, you can reduce it to like 70 to 80% or 60%. And also the pattern of the infill also matters. So the honeycomb structures provide a very good strength into the structure for the infill density. So into our software solution, into our 3D printing solution, we have different kinds of the infill patterns also available, which can help the user to decide what kind of interior strength or what kind of stresses acting on the part, which can be dispersed by reducing the infill density and also by applying a particular infill pattern. So for the printing strength, more shell thickness will provide a good outer strength, but for the interior stress disperse, the infill density also matters and its pattern also. So honeycomb pattern with a infill of like 50 to 60% and with a shell thickness of like around a 2 mm to 3 mm will provide a good structural integrity into the component, depending upon the geometries and their sizes.
Okay, thank you. I think that that answers the questions. Any other questions from the participants? So there is one more question. What is the shelf life of 3D printed materials? Like, what is the life cycle compared to that of traditional, any material manufactured using traditional method?
Okay, yes, sir. So with the shelf life depends upon what printing technology or what material you are using. So for the FDM technology, if I talk technology, all the materials are thermoplastics, which are basically similar as we see into the industrial market, like the ABS, polycarbonate, nylon material, PP material. So these kind of the thermoplastic materials. So the shelf life is similar to what we get from the injection molding process or with other plastic manufacturing processes. Because the material which are being used are the virgin materials, so these are not the mixed material or the you can say uh, or damage to some air or the moisture. So the shelf life is similar to what we get through the injection molding process. So that's why these thermoplastic 3D printed parts can be used as an end use part, and these thermoplastic 3D printed parts are being used as an end use part into the automotive and into the aerospace industry and also into the space industry. Okay, so like ISRO, NASA, they are using the Stratasys solutions to make the end use parts which are being fitted into the space shuttles or for the rocket, and also in the mobility transportations, like I've shown you some examples for interior and exterior. So the final produced part, so the 3D printed parts can be used at the end use part because they provide the same structural integrity and the same shelf life and a very good quality with high strength, similar to what injection molding process or other plastic manufacturing process can provide.
Okay, thank you.
Hello,
Yes.
this is Mayank.
Yeah, please go ahead.
I'm interested to share my experience over the 3D printing and CNC machine, means lathe machine. Can I go?
Yes, sir.
Yeah,
Yes.
yeah, please, please.
We have used same thermoplastic material for 3D printing as well as lathe machine. We manufacture pneumatic fittings, right?
Okay, sir.
Whatever fittings we use for the pneumatic connection for polyurethane tubes. So after made of these fittings, we try to test the strength, compression, and temperature effect.
Yes, sir.
Same material, but whenever we test with the lathe machine or CNC machine produced fittings, that were find less strength than the 3D printing machine fitting. Same temperature effect, the fitting was more able to face the high temperature than the lathe machine prepared fitting. Chemical chemical properties is almost same, but the strength wise and compression wise, 3D printing machine fittings having the more strength compared to the lathe machine or CNC machine prepared fittings. So that is the difference between the conventional style of the manufacturing and 3D printing fittings. Just this is our experience in past time. We have conducted this in the Instrumentation Research Center in Uttar Pradesh Institute, whichever falls under the Instrumentation Society Skill Council in Bagpat.
Okay, sir.
Thank you, sir. Thank you for sharing that information.
Yeah.
That's a very good experience, sir, to share with us. Thank you for sharing it.
Any other questions from the participant side? Any queries, any questions? Just a last question. I think it has been posted multiple times. We can see 3D printers that are being sold off the shelf. You can place an order over Amazon. You can place an order over Flipkart. They are all available on such websites. And then there are industrial grade 3D printers which may cost from several lakhs to crore. So what are the differences, in terms of course, it depends on the resolution, the print volume, and all those things. But in general, what is your experience in terms of, what will be the basic difference between these cheap 3D printers compared to that of industrial grade 3D printers?
Okay, sir. So the basic difference that we find between the desktop or the low cost versus the industrial 3D printers. With the low cost 3D printers, it does not provide an easy workflow because it is just a machine assembled with the assembled components. Okay, so there are no specific control features, or there is no specific integration between the machine and the software you're using, okay, to control the machine or to slice up the parts. Low cost 3D printers, we have the softwares, but these machines are not optimized or are not integrated properly with those softwares. Okay, so first is your process control features are not optimized. Okay, so it impacts on the strength, it impacts on the printing process. Okay, it tends to part failures a lot. Second is, even if your prints get successful, so the materials which are being used or which are available into the market are being of not a very good quality. I won't say a cheap quality, but I would say it does not provide a very good quality for that material. If you're using a low cost or an open source ABS material, it would not provide a very good strength as compared to the industrial grade machines material. Because first of all, its printing process, it's not in a very much controlled environment. Second is, even if your part gets success into the low cost machine, it would be just for the part validations or for the prototype validations. I mean, You can just check it for the design validations. You can check it for the form and fit, like fitment between the two parts. But the material itself will not be that much of capable to test out for the high functional properties. Okay, so like Mr. Mayank has shared us this his experience. Uh, those kind of materials which can withstand or which can provide more strength comparative to the conventional manufacturing process. It depends on what kind of machine or what kind of the process control features and the material properties are included. So with the Stratasys machines, they provide the industrial grade machines with more than 1400 plus patents. They have a very good process control features, which provides a very easy workflow and a very good integration between the machine and their own software, which is a GrabCAD print, so that the user doesn't have to get worry or babysit or monitor the printing process all the time. You can run the industrial grade machines 24/7, but with the desktop or the low cost printer solutions, I mean, they are not good to run 24/7 because their components are also not of very good quality, because the cheaper the machine, the cheaper the components will be used. So it would not be very good in long term run, but yes, you can use it for the initial running process, or just to make a fewer prototypes, okay, or just a hobby printer. So we call it the machines which are sold on websites like Amazon or Flipkart, or as an open source machine, we call it as hobby 3D printers. Okay, hobby 3D printers where you can purchase, you can keep it in the house, and you can do learnings and you can do some design developments for your own applications, for your own use, but not for the industrial applications or for the industrial purposes. So that is what basic difference between where we find out between the desktop grade or the low cost printing solution versus industrial grade solutions. Thank you, Prashant sir. Thank you, all the participants, for being a patient listeners and for very good questions you have put up. Thank you for this session to happen, and a very good day to all of you.
What will be the quiz duration? Okay. Because of total full day engagement with your this presentation, uh, most of participants need some time. No problem. Okay, sir. Okay. Thank you.
Thank you, sir. Thank you, NMIT team and all the participants. Have a good day to all of you.